So welcome back guys. We are now going to start looking into the Hooke's law for shear stresses and shear strain. So far what we have established is what is the Hooke's law for the normal stresses and normal strains. Now we are going to establish something similar for shear stresses and shear strain. So just like from the tensile testing experiment which we had seen that the normal stresses and normal strains are proportional to each other until the yielding is reached. In a similar way, if we plot the shear strain versus shear stress through a torsional test experiment, I will not discuss with you the torsional test experiment because torsion is not there in your syllabus. So just for the sake of completeness, I am saying that if you plot the shear strain with increasing value of shear stress using a torsion test equipment, you would observe that the diagrams are something similar to the normal stress strain diagram. So you would see that the initial portion of the shear stress strain diagram is also a straight line. Therefore, my shear stress is proportional to my gamma. In other words, my shear stress is equal to gamma, 1 by G into gamma, where G is known as the shear modulus and sometimes it is also called the modulus of rigidity. So, in shear stresses, each of the components are only dependent upon I'm sorry, this has to be equal to G times gamma, not 1 by G into gamma. So all the shear stresses are going to be dependent only on the corresponding shear strains, and they are not dependent on, gamma xy is not dependent upon tau xz and so on and so forth. So keep that in mind. Let us solve one problem which will complete this example. So you have over here a rectangular block of material whose modulus of rigidity, that is G, shear modulus, is given to you as 90 ksi, and it is bonded between two rigid plates shown here and here. The lower plate is fixed while the upper plate is subjected to a force P, and knowing that the upper plate moves through 0.04 inches under the action of the force, you have to determine the average shear strain in the material and the force P exerted on the upper plate. So you see, we know that the shear strain is the change in angle. It is given to you what is the length, which is given as 2 inch, and it has moved by an amount 0.04 inch. So gamma xy, which is nearly, if you focus your attention to this small triangle, so gamma xy is, since gamma xy is very small, you can say this is equal to tan gamma xy is equal to 0.04, which is the displacement by the original length of 2 inches. So you can find out the shear strain directly. Now in order to find the force P, since G is given to you, you have to first find out the shear stress and multiply the shear stress with the appropriate cross-sectional area. So the shear stress is tau xy, which is equal to G times gamma xy, from which you can compute the shear stress on the top face, and this shear stress is equal to P by the area A, and this area is going to be this area on which I have drawn this shade. So shear stress is going to act in that area. So P, the force, is going to be equal to the shear stress times the shaded area, and that gives you P value to be equal to 36 kips. So let us now look into the relationship between E, elastic modulus, and G, the shear modulus. So remember the case which you must have studied in your when you were studying the stresses part. So you would see that sigma x, I have an axially loaded slender bar of a uniform cross section area, and this is being pulled by a force P, and the stress sigma x along the axis of the bar is equal to P by U. But if I now focus my attention to a cross section which is inclined at a 45-degree to my x-axis. So this is my original cross section. Now I am going to focus my attention on a cross section which is inclined 45 degrees to my x-axis. And if I plot my shear stresses and the normal stresses, I see that at 45 degrees my normal stress is equal to P by 2A and my shear stress is also equal to P by 2A. Therefore, under purely axial loading, you can get not just normal stresses and normal strains. You will also get shear stresses and shear strain. That is, both shear strain and normal strain will arise under the application of purely axial loading. So let us now extend this concept into a slightly different thing. So consider over here the same cubic element of unit dimensions, and let this cubic element be subjected to an axial force P, due to which the dimension changes from one dimension change to 1 plus epsilon x and 1 minus nu epsilon x in the y direction as indicated here. Okay, now focus your attention to the plane which is formed by the diagonal of this cube. This diagonal is going to be inclined at 45 degree, right? So this diagonal makes an angle of 45 degree with the x-axis before the loading is done. But after the loading is done, it is going to make an angle which is not equal to pi by 4, which will be different from pi by 4. In other words, there is going to be some shear stress which is going to arise here. So this shear stress beta, or the shear strain, can be related to the angle beta through pi by 4 minus whatever is the shear strain here, right? So beta is going to be equal to the original angle minus gamma m by 2, and I also know if I now apply the expression tan of alpha minus beta or x minus y, this expression if I now apply, so I can see that tan beta can be expressed in terms of gamma m, which is the shear strain at the 45 degree plane. But from this figure also I can see that the tan beta is equal to perpendicular by base, that is 1 minus nu epsilon x by 1 plus epsilon x. Correct? So if I now substitute the values, of uh, uh, gamma m from here, and tan beta equal to this quantity, and then gamma m from here which I substitute, I can see that the gamma m, the shear strain, is equal to 1 plus nu times epsilon x. But I also know that epsilon x is related to sigma x, and that is equal to sigma x by E, and gamma m is related to the shear stress, which is equal to tau m by g. So if I substitute these two relationship of sigma epsilon x here and gamma m here, I can see that I have the relationship between E by G, which is equal to this quantity sigma x by tau m. Now remember, sigma x and tau m how are they related? Sigma x is only along the x direction, but tau m, as we had discussed just before, tau m is nothing but it is equal to half of the shear stress there, half of the normal stress there. So this quantity is twice, from which you get the relationship that G is equal to E by 2 into 1 plus nu, and this gives you the lower limit of nu as well. Okay, so let us solve one problem, and after that this class will finish. So we have over here, we have in this problem a circle of diameter d. It is ascribed on an unstressed aluminum plate of thickness 3 by 4 inches. The forces are acting in the plane that cause normal stress sigma x and sigma z. So sigma y is 0. Elastic modulus is given to you, Poisson's ratio is given to you. Find the change in the length of the diameter, another one, the thickness of the plate and the volume of the plate. So all these quantities are written. And this question tells you that you have to use the generalized Hooke's law over here. So since sigma y is equal to 0, we can find out the strain in the different direction. Epsilon x, from the generalized Hooke's law takes a form of this kind, but since sigma y is equal to 0, I only have now sigma x and sigma z in the picture. Similarly, I can find out epsilon y and I can find out epsilon z using the generalized Hooke's law. Okay, so I can find out epsilon x, epsilon y, epsilon z through the generalized Hooke's law. Now, in order to determine the change in the diameter, I have to find out the diameter AB. I have to find out the relative change of location B times with respect to the point A. This is something which I have to find out, and this will be equal to nothing but the strain in this direction multiplied by the original diameter here. And the strain along this direction is nothing but it is equal to epsilon x. So this is how I find out the change in the diameter AB. Similarly, for the diameter CD, what I have to do, change in the diameter CD, I have to find out the strain along the diameter CD and multiply it with the value of the diameter. The strain along CD is nothing but it is equal to epsilon z. So my change in diameter is going to be epsilon z times CD. Similarly, for the thickness, I have to now work with the epsilon y term. The change in the volume is nothing but the volumetric strain or the dilation that we had talked about, delta V by V. So if the dilation quantity is E, it is equal to epsilon x plus epsilon y plus epsilon z, and that gives me the total change in the volume. Okay, thank you guys.